Okay, I don't know if you guys got my message or not. I hope you did, but the Friday, I haven't been able to get the Friday recording to work. And for some reason, although I have 3 computers here, when I turned off, turned one down computer, it knocked the recording off of the other machine it was being recorded on. Don't know why. Okay. You guys have a test due tonight. And some of you, I guess that's for everybody. Some people have a test due Monday or Wednesday, I believe. Now, there are 2 people who have taken the test for that's due tonight, and I can't give you your test back yet, but the 2 of you who took the test already and put it on Blackboard as of last night, I have graded your test and you both passed, whoever you are. So I thought what I can do now, as soon as somebody turns in a test, I can grade it. The reason is so that you'll get as early a notice as possible as to whether you need to take a retake. And so if you get the test to me, I'll try to grade it as soon as I can. Now the retakes, this doesn't have to be such a hurry because there's no retake of the retake. But the test that I guess is due tonight, that's the one that you could take a retake over. And so I'll try to get those done as soon as possible. Another piece of business, what about tomorrow and when and so forth? What about in class, on campus? Do you want to keep doing this, or do you want to go back to being on campus this week sometime? Now, last Tuesday, I believe, for this class, 1 or 2 people showed up. And so Tuesday's not a high mark for us anyway. What about tomorrow? Anybody need to go to on campus, or is this okay? So I have one person saying this is fine. What about the rest of you? Anybody have any need to be on campus for what we've been doing?
I personally don't care.
Okay. Well, the big decision has to be for Wednesday because that's when the other class has to know as well. So tomorrow we'll do it remote unless somebody needs to be there. It's good for me to do it remote only because it saves me about 3 hours of driving back and forth and getting the class ready and all that, which I can devote to grading tests, for example. I also have 2 searches for, one for a new faculty member, one for a secretary, and there's meetings all the time, all this week about that. And so for me, extra time is in short supply. So it's helpful to me if we do this remotely, but I don't want to disappoint you guys if you feel you should be there. Anyway, tomorrow will be remote. And so just a second here, I got a message from someplace that I've got to refer to here. Just a moment. Okay. So things went blank for me for some reason. Okay, so now I thought we might start, we were doing integrals the other day. I thought we might do Thank you. I see two people in the chat said something. If I share the screen here, just a couple integrals I thought might be interesting to you, because all that people are trying to do with these integrals is try to mix you up in terms of what you should do. And the thing here with this problem, it's nasty. And let's sort of explain why it's nasty. If I would let u be 1 over x, then du is minus 1 over x squared dx. Now, if this down here were x squared, this would be exactly what I want to do. So let's do that problem first. Let's suppose I had cosine 1 over x squared. Then I would do a substitution, u equals 1 over x. Du would be minus 1 over x squared. Dx, don't ever forget. And so I can replace this, the minus I can input in, and I can replace this with minus the cosine of u du, which is minus the sine of u, and you put back in the 1 over x. And so that problem would be relatively easy to solve. And basically what you're looking for is the inside of a composite to substitute for. The inside of the composite I see here is 1 over x. That would be the idea to substitute for. Now, that's the prototype. That's what you think should happen. If you try to do that on this problem, it doesn't work. So what is the wise thing to do with the x squared down here? Remember that whenever you substitute, the derivative's got to be there. Well, the trouble is I got an extra x here. When you have an extra x, you don't just ignore it or put it outside or decide you'll deal with it later. You got to work with what it is. So maybe what we should do with this problem is an integration by parts. Maybe I should view this as 1 over x times the cosine of 1 over x squared. Why? Because I know how to integrate that. So if I do that, then I'm letting u be 1 over x, and I'm letting dv be cosine of 1 over x squared. And because I don't want to ever forget the dx, you always put the dx. Then the v I already solved. The v is minus the sine of 1 over x. Now, whether this is the way to go, I don't know, but I get rid of this nasty stuff. But this du, unfortunately, is still nasty. But it's okay, because when I do my uv, that's minus 1 over x sine 1 over x minus v du. It's minus, minus, minus. There's 3 of them. That's going to end up with a minus. It is dx over x squared sine 1 over x. And it's x squared. So now, okay, I could do cosine x squared. I can do sine x squared. So this is the way to go. Now I got to do this one, but this one's substitution. Substitution is u equals sine of 1 over x. Then du is minus 1 over x squared dx. And this minus is taken up this time. So in the end, I have minus 1 over x sine 1 over x. That's copied. The minus becomes a plus because I'm going to use up the minus with the du. I've got to integrate sine of u, which is minus the cosine of u. So the minus comes back again. And I'm going to have the cosine of u, which is 1 over x plus c. That's how I would do that problem. Okay. If I have something like this, a quadratic on the denominator, what you try to do is factor. In this particular case, I can factor. Okay, once I can factor, then this becomes a over x plus 4 dx plus b. It becomes a partial fraction problem. And you know how to solve partial fraction problems. So if it's like that, if I can factor it, that's what you do. What if, and I'm making this one up now, the other one I got from the book, what if it's x squared plus x plus 1? Now I can't factor this. I mean, I can factor it, but they're complex. So what you do is always when it's like this, you complete the square. Completing the square is adding half of this to half x and so forth. And what it boils down to is, you know, you take half and you square that. And so this is going to be x plus a half squared. When I rewrite that, that's x squared plus x plus a fourth. So I have to subtract a fourth and plus 1. So what I'm going to get here is x plus a half squared plus 3/4. In other words, when you complete the square, you get the sum of squares. Now, the x plus a half is a square. Well, the 3/4, I don't see a square, but what you do is you write that as the square root of 3/2 squared. And by the way, the half and the square root of 3/2 ought to remind you of something, namely the sine and cosine of 30 and 60 degrees. And it turns out that the actual solution of this equation in a complex plane, the roots of these things occur in, on the circle here, and there's a certain angle, and the angle is going to involve 30 or 60 degrees. So you're going to get two roots out of this thing, and they're going to occur at places like this that involve 30 and 60 degrees. I'm not going to worry about that right now, but that's why when you see a half and square root of 3/2, you ought to know that 30 and 60 degrees of something is involved. Okay, well, what I have here is x plus 2 in the numerator. I haven't done the integration yet. All I did was change the denominator. So now what do I do? Well, it's kind of nasty. But when you have a sum in a numerator, you want to break it up. And so I'm going to this mess now. I'm just rewriting it. But the 2 is now easy. The 2 part. The constant part is easy because what I see for the rest of it here, and I ran out of paper and off the screen, this is an arctangent. Now, it's the sum of squares. That's going to be an arctangent. Now, you might have to shift first to do it, but that's going to be an arctangent. And so if you remember the 1 over x squared plus a squared, now you may have done this enough to remember that's 1 over a. Somebody else want in or anything, by the way? You should go look and see. Anybody else want in? I think everybody's here. Okay. Anyway, it's 1 over a arctangent of x over a plus c. So I'm going to have to invert this square root of 3/2, and I'm going to have to put it in here, and I'm going to have a shift. And so this one is going to be 2 times. Now, the a in this case is the square root of 3/2. So it's going to be 2 over the square root of 3 when I work that out. And I'm going to have the arctangent of 2 over the square root of 3 times x plus a half because of the shift. So when you do this, the thing here, if I have something else on top, I split it up and one of them becomes an arctangent formula. The other one, well, I don't know. So I'm going to go back for the other one to the original. And the original was x plus 2. And so if I look at the original, maybe I wasn't such a smart guy after all. If I had 2x plus 1 in the numerator, if this is what I had, then I can do an integration by substitution. This is u, this is du. I have a logarithm involved. So, well, unfortunately, I don't have that. But I did split it up. I got rid of the 2, and I have this x thing. So that x, if I make it 2x and divide by 2, I'm trying to create something that I can deal with. And I need a plus 1, so I subtract that. Now, that means when I do this now, I'm going to have a half of 2x plus 1 over x squared plus x plus 1 minus 1 half. And that's the same kind of thing I dealt with a minute ago. So what I now see when I do this, I can do this, but I should have left the 2. I should have played with the 2. So I'm going to do the problem over again now that I've learned. And that's the whole idea here, is to learn something as you do these things. And so when you have something like this, x plus 2 over x squared plus x plus 1, the first thing you ought to do is try to make it so that you can use substitution. And that means I need to have a 2x plus 1 dx. Well, so what you do is you say, okay, I'm going to make a 2x and divide by 2 there. Now that's all inside, that's not outside. And I'm going to steal, well, if I take the half out, that would make this 4. Because a half of 2x is x and a half of 4 is 2. So I now have a half outside. I think that's a good idea. And I have 2x. I need 2x plus 1. So I'm going to have a half the integral of 2x, and I'm going to take from the 4, I'm going to take a 1. And that's going to leave me with 3. Now, on the other side of the thing I turned over, I had a plus 2. That's what we did. We split it up. That was still a good idea, but now I'm going to split it up. So I have a half 2x plus 1 over x squared plus x plus 1 plus 3 halves 1 over x squared plus x plus 1. Now this is just, I can write down the log of absolute x squared plus 2x plus 1. And over here, this is an arctangent. We already did it. We already know what this is about. It's 2 over the square root of 3 arctangent of, in this case, it's a 1. The 1 here is and so forth. But anyway, it's 2 over the square root of 3 times x plus 1. If you remember, x plus a half plus c, I believe was correct. So sometimes you try doing something, and hopefully as you do it, you think, oh, I should have done something else. But that's okay. That's part of the learning process. And so that's, I'm hoping that these little ideas will help you guys sooner or later in what you're doing. And so there's a whole list of problems here, and on the next page as well, some of which we did. I don't know if any of you have been working any of them, and let's talk about that for a second. I noticed that some of you are doing WebAssign problems in chapters 10 and 11. Other people haven't done that yet. Remember that the number of points from the tests is not enough to give you an A. You need to have a few more, and in some cases, a lot more. I highly recommend if you want an A that you do problems in WebAssign. And it's a win-win situation because if you do, it'll help you on the final and maybe on the test that's due Wednesday. Anyway, if I look at some of these others on here, I see some stuff that just I don't know if I want to handle or not. Here, let's see about that one. I don't know how to do that one. That's the square root x times the square root of 2 minus the square root of 1 minus x squared. Now, that looks nasty. What should I do? And I have no idea. Seriously, I have no idea at the moment. But if I let, again, substitution is what you think first. You want to look for something inside. And this is 1 minus x squared. So I'm going to guess here. I'm going to try the square root. No, just 1 minus x squared. The reason I have this x. Then du is 2x dx. Now, I'm not going to do a definite integral. I'm going to do an antiderivative problem. So I'm going to rewrite this, and later, once I find an antiderivative, then I'm going to go back and stick in endpoints. So just doing this, just to try to hopefully simplify it a little bit, I need a half, because if du is 2x, then x dx, which is what I've got, that's a half du. So by what I've written here, a half du, I've taken care of x dx. And what have I got left? I've got 2 minus, well, if this is square root of u, so this is u to the 1/2. Now, that's not nice, but it's better because I don't have any product here, and I don't like this u to the 1/2, but it's better than the original problem. This looks simpler than the original problem. Now, how am I going to solve this? I don't know, but it now sort of looks like a trigonometric substitution of some kind. And if I do that, that's with a theta, usually something like that. And what do I put on the, this is nasty. What do I put, how do I make a square root thing? I would put what? I'm gonna have to make a triangle. And what I'm used to seeing with a triangle is a square minus b square, something like that. And that's when I put a on here and maybe b over here. So what would I have to put on here to make that? I have to make a square root of 2. And I have to make a u to the 1/4, I guess. If I did that, then when I square this, I get 2. When I square this, I get u to the 1/2. And that makes this down here 2 minus u to the 1/2. So this is kind of nasty. But the cosine of theta is the square root of 2 minus u to the 1/2 over the square root of 2. So if I multiply that, I get this. If I take a derivative, I get minus, I get sine theta d theta. And if I take a derivative over here, well, that's kind of nasty. So to get to du, I've got to do that. That's going to be 1 over 2 minus u to the 1/2 times the derivative inside, which is minus a half u to the minus 3/2 du. And so it seems to me that I'm getting worse and worse, except maybe not, because if I look at things, I may be able to salvage some of this, because this 1 over this, that's a secant, more or less. And this u to the minus 3/2, well, that may be something to do with sine. And so I need to try to utilize things. So what do you think? Do you think we should keep going with this, or do you think we should try something else? This is, I got this place because I made this substitution. Maybe I should have done integration by parts. But if I do an integration by parts, I have to decide which is u and which is dv. If I make this dv, I got to integrate it. Well, we don't know how to integrate that. That's what we're dealing with right here. If I make this u, then I have to differentiate it, and that sounds bad. So I don't think integration by parts is going to be the game. So what do you guys think? Is this a particularly nasty one? How would you solve it? I'm waiting just because why not, you know? You have any better idea than what I've done already? And if you've got your books and stuff, what problem was this? This was, oh, I've lost the place where I came from here. Was this an even problem or an odd problem? It was 48, of course. It was an even problem. So you can't even cheat unless you really cheat by having the answer book. And so sometimes what people do is they don't know what to do, so they fudge a little bit and look and see what they think the answer is. And it's like, oh, now I see how to do it. Well, that's not a bad thing to do either while you're learning. If you get stuck, you need some assistance. The whole idea is you use the assistance you have. And if it ends up by looking at the back of the book a little bit, that doesn't matter as long as you learn from it, because it's not a test. You're just trying to see if you can do it. And the idea is to learn so you can, if you get another one like it, you can do it later. Okay? So it's awfully quiet over there. Anybody coming up? Should I have done something different, what you see on the screen? Or is this good?
I don't know if it matters, but with the original u statement, isn't it supposed to be 1 minus x squared, which would then change the sign of the u throughout?
Yeah, did I do that wrong? When I look here, looking at the page, should this have been minus?
I think so.
All right, so that should have been minus there. Okay, so that messed up the whole thing. Okay. So, and now I don't, so I'm sorry, I did not do that on purpose. This should have been minus there, which should have made this minus 2x. Now that doesn't change much here. That just makes a minus. When I change it here, it's going to make a minus here. That doesn't change the rest of it. Okay. So if that was your question, that's just a mistake on my part. But when I put it in here, in other words, I made a mistake writing that right there and I didn't put a minus. But right here, when I replace that with u, this is not wrong from here on. Okay. But I don't know if that's the right idea. Okay. So what about trying, because it's got into this u to the 1/2. What about trying u is the square root of 1 minus x squared? See, it's still inside. So I tried to go way inside here. What if I didn't try to go quite so far? Well, then u squared is 1 minus x squared. So 2u du is minus 2x dx. So u du is minus x dx. Because I have an x dx. So let's try this and see. So the idea there was I tried to do something all the way inside there. That got me a little bit messy. Let's try this and see what we get. This will be 2 minus the square root of 1 minus x squared. And the x dx becomes minus u du. That's this part. And the rest of it becomes, I don't know, square root of 2 minus u. Okay. That's okay. Now, you may not think it's okay, but I think it's okay. Why is it okay? Because you've seen problems like this. If you let v be 2 minus u, then u is 2 minus v. Okay. So anyway, du is minus dv, and the integral up here becomes, I use the minus du for dv, and I switch to 2 minus v square root of v, because 2 minus u is v. And so I have the integral of 2 square root v minus v to the 3/2. The point is I can now do that. The square root becomes 2/3. I get 4/3 u to the 3/2 minus the 2/5 v to, that's a v to the 5/2. So then I replace the v with the u, and I have 4/3 2 minus u to the 3/2 minus 2/5 2 minus u to the 5/2. There'll be a plus c in a little while. And then the u was the square root. So in the end, you can copy, it's just a copy now. 1 minus x squared, 3/2 minus 2/5, 2 minus the square root of 1 minus x squared to the 5/2, if I didn't make any secondary mistakes. But the idea there is, I tried something and it got me in the worst mess, and I wasn't quite sure what to do with all this. So sooner or later you think, well, I don't like this. Maybe I should try something else. What else can I substitute for? What's another inside? Another inside would be that whole thing. I don't know. It doesn't seem like it's going to work. So I try it. And because of this, it does work. It gives me an easy way to translate, which makes something easy to do. This is, I consider, easy. Once you get to this stage, you should be able to see how to switch it around so that you can do this right here that I did at the bottom. Okay, so I'm hoping that that kind of thing is enlightening, but you ought to work them. I mean, and those of you who don't do this very much won't understand this, but there is a satisfaction gained from conquering these things. And now, I have no idea what to do here, but what do you know about x log x minus x? That should, you should.
Integral of log.
That's the integral of log, right? That's the integral of log. Now that's in the denominator, but that's the antiderivative of logarithm. I wonder if that's relevant with that one, but that's what, when I look at that, I see if I would differentiate this, I get logarithm. Now, with integration by parts, we integrate and differentiate, see? Except the trouble is this is in a denominator. But just looking at stuff, I see that. And so I think that that's something I could weave into things. What would happen if I'd let u be the whole denominator? Then du would be log x dx. Well, I don't have a log x upstairs. But anyway, I'm not going to do that one for you. This is just an idea, but when I look at it, that's what I see. What do you see here? If I didn't have the x, I see an integration by substitution. If I didn't have the x, I'd let u be 1 plus e to the x. Then du would be ex dx. Since I do have the x, I think integration by parts. I'd let u be x and dv be the rest of it. That's what I would do. Okay. So have we done enough integrals for a while, or you want me to do more, or what? Because a couple of days ago, people want me to do some integrals. Some of these can be, quote, fun. You have to think of it that way. By the way, on that problem, I didn't ever do the definite integral. When you do an antiderivative, but you're doing it because you have a definite integral, don't forget the definite integral. Because at the end, when I get all done, I'm supposed to substitute stuff. You go to all that trouble to get the answer, then you forget to do the actual original problem. So you don't want to do that. So anyway, how about series? How are you doing on series? Some of you haven't done much in terms of WebAssign yet. Do you want me to talk a little bit about series today, or do you not? I'm just.
Please do.
Yes, anybody?
Please do.
On the series?
Yes, please.
Okay. By the way, on this one, wherever you are here, what you want to do here is actually make u log x minus 1. If you make u log x minus 1, not log x, but not this whole thing, but just log x minus 1, then du is 1 over x dx, and it's easy. So I don't want to leave that for you too long. So in other words, this doesn't look like a product, but it is in the denominator. It's x times log x minus 1. Anytime you have a log involved in an integral, you ought to be thinking of 1 over x as a derivative. And so if I let u just be log x minus 1, then it becomes easy. If you do what I saw about some kind of log thing, that's not so easy. But you want to be hit with an idea and try it. And if it doesn't work, don't quit. Don't say your mother never said you'd be a mathematician. Don't do something like that. Just say, hey, that didn't work. Let's try something else. Okay. And so, okay. If we go to series, when we get up to series here, you have series of constants, series of power series of x's. You have sequences. Which would you like me to talk about? Series of numbers, series of x's, or sequences?
Sequences.
Sequences, okay. Well, with sequences, don't confuse some of the things about series. And what I mean by that is that, for example, when you have a series, and let me get, since I have a screen here, let me go to another page. Because you spend so much time in the series, if I have this series, this diverges because it is called a harmonic. That's not why it converges, but it does. And when you have a convergent series, the terms go to 0. Like these terms will go to 0. But the series diverges. Now, if we're not talking about series, we're talking about limits. And if this is your question, then you just say 0. Okay. In other words, it's much less complicated than this is. In this case, the terms go to 0, but the series diverges. Anyway, with these things, you need to figure out what's happening. And you can do a squeeze on these things. For example, if I had n squared, now this is simple enough you wouldn't do it, but n squared is less than 1 over n, and that's bigger than 0. And so if this limit is 0, it's going to force this limit to be 0. So if you had something like the sine of n over n, that's less than or equal to an absolute value, 1 over n. And so since this one converges in limit to 0, this one will. Now, again, with series, it's more complicated because it's not just that these go to 0, but it's how they go to 0. Now, but with sequences, and what we can do is go back to the sequence section. And we'll find it here. Okay, there are certain theorems that we used with sequences. One of them was if I have a limit and it's just a simple power, then what's inside here determines whether it converges or not. And the key is whether or not the thing in here is bigger than 1 or less than 1. If it's a constant, it's some fixed thing, whatever, not an x or anything, it's a fixed number. So whatever this number is, if it's minus a half or plus a third, you go to 0. If it's plus or minus 7, it goes to infinity. So it depends on the size here. Okay, that's one of the biggie theorems in this section. It is this number 9. If the r is a number bigger than 1 or less than minus 1, then you could diverge. If the r is 1, you converge, and if it's less than 1, it goes to 0. It's also converging. Okay, now there's something else about sequences, and that is if they're increasing or decreasing, sometimes you can time whether they converge or not. And so this page on the author's part in 741, that has to do with increasing or decreasing sequences. Now, if an increasing sequence is bounded above, it will converge. If a decreasing sequence is bounded below, it will converge. Okay? Otherwise, they will diverge, both of those. Now, you can also get divergence if you have things oscillating, like +1, -1, +1, -1, and we're not adding them up, we're just asking where do those go? And the point is they don't go to anything, they go to two things. They go to +1 and they go to -1, therefore there's no limit. But if it's increasing or decreasing, you will sometimes know there's a limit even if you don't know what the limit is. Okay, so that was an important theorem in that section, which helps you. If we go to the page of problems here and just look for something, some of these, like if you look at something like 31, what happens to 1 plus this and so on? Well, first of all, you don't worry about square root in terms of whether or not the thing exists or not, at least not yet. What I would do, since n is getting big and you got n's in the numerator and denominator, I would divide by n squared and change the look of this to 1 over n squared, which is going to go to 0, plus 1. No, plus 1 times 4. So the numerator, if I divide by n squared, is going to go to 4. The denominator, if I divide by n squared, is going to go to 1. So this is going to go to 4 over 1. Then I do the square root. So the answer to this one is going to be 2. Okay. What about something crazy like n pi over n plus 1? Well, n pi, 1 pi, 2 pi, 3 pi, and so on. That's not what I've got because I got to divide by n. So when n is 1, I have pi over 2. When n is 2, I have 2 pi over 3. When n is 3, I have 3 pi over 4. What's happening here? Well, if I would inside here, let's see if I can write out this. If I would look at the inside here, n pi over n plus 1, and think of this as n over n plus 1 pi, then the limit of the cosine of something is the cosine of the limit, because the cosine is continuous everywhere. So if a limit exists, the limit of the cosine is the cosine of the limit. And so I can go inside and look at what happens here. Now it's not such a big problem because this is going to go to pi. So the whole thing is going to go to cosine pi, which is -1. So when you have continuous functions involved, you can take the limit inside. And that's what makes this one easy. If I have like something like sine n, what's sine n? Sine 1, sine 2, sine 3, sine 4. I don't have any idea because that's going to jump all around. Sine n is not going to have any limit. Every once in a while, it's going to be in the second or third or fourth quadrant. And as you keep going higher and higher, it's just going to keep jumping around. So anyway, that's going to be one that doesn't have a limit. What would you do with log n plus 1 minus log n? If I have log n plus 1 minus log n, well, every once in a while you need to use a formula. And that's the same as log, not divide here. That's the same as n plus 1 over n. And that's the same as 1 plus 1 over n. So this is going to go to 0. Why? Because 1 plus 1 over n goes to 1 and log of 1 is 0. So again, once you get a function here, the function's continuous, so you can take the limit inside. Limit inside is 1, then the answer is log of 1. Okay, so we're at 19 after here. So I think I'm going to turn off the recording. I don't think we can probably get another problem done here.